Can you hear me?
Yes.
Perfect. Thank you.
And we are live.
Hello, and welcome to today's webinar, Get It Right the First Time. This is Marcia Tucker, Simulation Specialist at Applied Software, and I'm delighted to be your moderator today. We have asked our Simulation Specialist Master Graphics to join us on this webinar. They're located in the Upper Midwest and also have great longevity in the Autodesk channel. Throughout our presentation, we encourage you to interact with us by typing in questions and comments using the questions pane. We'll be answering your questions at the end of the presentation. By the way, this webinar is being recorded, and you will receive a follow-up email with a link in the body of the email. We have several contributors today, and the first will be Mike Schultes. He has over 25 years in the manufacturing sector, with 10 of those at Master Graphics. Providing our technical expertise today is Mark Huntoon, Simulation Solution Engineer at Master Graphics, and holds multiple engineering degrees. And if you will go to the next slide, please. And the next one, yeah. Here's a little bit about Applied Software. When you search us on YouTube for the Live Lab Learning is where our recording will be, along with other pre-recorded webinars. And as you can see on the next page, Applied Software has a single focus, helping our clients achieve high performance. We are an authorized training center, along with being a platinum partner of Autodesk. We are an expert in manufacturing, mechanical engineering, digital prototyping, and data management. My contact information is below at 404-564-1870, and my email is marcia@asti.com. Master Graphics is one of the select few in the United States that is simulation specialized. They can assist you with digital prototyping from the very beginning of simulation, going through all of the steps, carrying it to the end of managed services. And now I welcome Mike to the presentation.
Thank you, Marcia. We all know today our companies are facing greater competition. So we've gone out and talked with many manufacturers about the challenges they're facing, whether it be cost reduction, regulatory compliance, labor utilization, or global competition. We're facing more and more challenges every day. So what are some of the business strategies that we've found customers are deploying to gain greater market share, greater sales, but more importantly, greater margin for their companies? And we've really found that a lot of companies are looking to differentiate themselves through innovation, be able to customize their products for their particular customer or market, and also compete in a global market. So let's look at, this whole discussion is why simulation. And it's really important that we share what we're hearing from clients on what best-in-class manufacturers are doing. So we want to share with you what we see as the traditional product development cycle. Whereas you get later in that, that timeline of product introduction, changes, it's harder to make functional changes. The cost of design changes increase. All the while, traditional testing being held where those 2 points come together. But what we're seeing and talking with customers about is moving that test and validation earlier on in the design process. using simulation, best-in-class companies are able to simulate early and often. What does this mean? And why is this important? Because if you look at the upfront decisions, design decisions, 70 to 85% of the costs come from design decisions that are made early on in the process. So it's critical that companies are using tools like simulation to properly validate those early design decisions so you could make those decisions early and often, moving the testing and validation phase. Certainly don't take it from us, but we do work with over 4,000 customers per year. And industry analysts are validating what we're hearing, is that in order to successfully take costs out of the products, engineers must be able to understand the trade-offs of performance and quality. And really, simulation are one of those tools and technologies that are providing answers to what those design decisions mean. As we work with clients, what we're finding are that companies that are meeting design product development delivery dates, meeting their design delivery milestones, are really using digital prototyping workflow, in that they're using simulation as a key component of that product development cycle to really test and validate that digital model early and often. We're also seeing a change in the typical product development cycle. Customer will do conceptual development. The product will move into the design phase to validate performance. Production will come online, and manufacturing will come up with the needed tooling and equipment to produce that product. And then the customer will operate, and hopefully it meets the customer's expectations, and the product will retire. That's really the traditional product life cycle that we see many of our customers following. But what's changing? What really is the future of making things? And why is that important? I'll touch on that. What we're seeing a lot of things in the next phase of manufacturing, or the next phase of the future of making things, is really product's value is really determined a lot by how well a customer can participate in the personalization of the product, or allowing consumers or customers, whether it be for an industrial machine, want to be able to participate in the configuration of that product. In the design phase, it's more important than ever to collaborate with extended design teams, as well as collaborate with people outside your business. Flexible manufacturing is more important as we see additive, like 3D printing technology, find its way down on the manufacturing floor, as well as subtractive that's more traditional. More and more products need to be connected, or companies need to be connected to their products as consumers use them to help see that revenue growth and being able to increase prices because of the extended capabilities of those solutions. Customers want things to be able to be changed or updated in the field, as well as products as a service are finding their way into non-traditional markets, offering greater business value to you and allowing greater innovation in the product development. So we see customers that are needing to move from the traditional product lifecycle, development lifecycle, to really a new product development process. Simulation is one of those tools that help support product information modeling and the future of making things. Now I'd like to turn the meeting over to Mark Huntoon.
Thank you, Michael. I'm going to quickly talk through the different Autodesk simulation products. We generally group these into 5 different categories, as shown on the slide: structural mechanics, flow and thermal analysis, structural architecture, molding processes, and composite materials. Obviously, the focus today is more on the structural mechanics. We do have 3 products that we support. We have Autodesk Nastran InkCAD, which is the embedded Nastran solver that can sit inside the CAD environment and with nonlinear analysis capabilities. The Nastran is a standalone solver that utilizes a separate pre- and post-processor, and then simulation mechanical, which we'll be showing you very shortly. Under flow and thermal analysis, we have a CFD product for fluids. We have a flow design where we can do a virtual wind tunnel. Under structural architecture, we have Robot, which is a code-checking structural analysis software for the large industrial and commercial and structural markets. We also can model injection molding processes through mold flow and mold flow design, as well as advanced composite behavior of advanced composite materials, and even tie that into FEA through the composite materials in the Helios products. They can also communicate with each other. Loading can be taken from CFD and brought into Sim Mechanical. Mold flow data can be utilized in FEA through Helios to gain accurate insight based on fiber orientation and density. Next slide, please. Now let's talk a little bit more in detail about Sim Mechanical. It's a powerful analysis tool that utilizes the Algor, and with the acquisition of NEI Nastran, Sim Mechanical now also has a Nastran solver built into it. So it can use that, or it can actually write Nastran cards and can be solved outside of Sim Mechanical. Specifically, it can do the following types of analysis: linear and nonlinear stress analysis. That's either with nonlinear materials or linear materials, variable loadings or static loadings. We can do advanced dynamic analysis. We can go beyond just the natural frequencies, but we can apply random vibrations in a frequency response analysis to truly understand what's going to happen to your structure or your part if it's subjected to a frequency or an operating load. We can do a critical buckling load analysis. We can predict when your components are going to fail due to buckling. We can do a fatigue life cycle prediction, and we're going to do that today. I'm going to show that to you. One of the really neat features is the deformable bodies, mechanical event simulation. We can actually go through and step-by-step show a deformable body and pull off stresses directly out of it while it moves through a motion. We can do thermal analysis, and we can do electrostatic analysis, as well as fluid structure analysis. And like I had said, we can pull in forces from CFD and from mold flow. So now I'm going to switch to, next slide, please. So the 5 things we're going to kind of hit on today is, first I'm going to have a discussion about the CAD neutrality of sim mechanical. Then I'm going to show you a fatigue life prediction study based on a circuit board. Then we're going to combine the mechanical event simulation and the impact loading. I have a simulation that I ran of a container that's on a flatbed truck that gets dropped. And then finally, we're going to talk about bolted connections. And once we're done with that, I'd like to spend a little bit of time talking about the 2016 version that just came out of SimMech. So we're going to switch to my screen. All right, so on my screen is Inventor. So the first thing I want to show here is within Inventor, there's a simulation tab once you install Sim Mechanical. And if I click on that, you can see right here, I have the Launch Active Model button. And I can press that, and it'll actually take my model data and pull it right over into SimMech. Now, we can do this not only out of Inventor, but we're able to do this with Unigraphics or NX files, with Pro-E or Creo. We can do it with Rhino. We can do it with SolidWorks, and we can do it with Space Claim. We're also able, if I come into Sim Mechanical, which is this is the interface, if I go to open, you can see right here as I go to the file types, I can pull in AutoCAD files, I can pull in CATIA files, Solid Edge files, and Parasolids. On top of all those other ones that I just mentioned that have a direct link into Sim Mechanical. So we also can go through the different interchange formats, such as DXF, IGES, STEP, and SAT. And we can go outside of Autodesk Simulation FEA and pull in those files. So regardless of your CAD package that you're using, we can open the data and we can perform the mechanical analysis. So I want to take a brief moment here, and I just want to kind of walk around the Sim Mechanical environment. As you can see, it's very similar to the Inventor environment if you're familiar with that. We have the ribbon where you can go through and you can set up your mesh properties. You can actually draw within it. You can set up your different constraints and your loadings and set up your parameters, which we'll show. And then you perform the analysis. You switch over, and there's a results tab for your browser. So you have an FEA browser editor, and then you have one for your results. And each one opens up a separate ribbon so you can get to your information quickly and efficiently. One of the things I did want to show here is in the 3D mesh settings, right off the bat, I can set up solid, I can set up midplane, I can set up plate or shell. If I go into options, I get all kinds of capabilities in terms of actually even setting absolute mesh sizes or even changing the as a relative, as a percentage. So right here, this is our first one. This is my circuit board, and this is the model that will undergo some mini thermal cycles during its useful life. So to determine the predicted fatigue life, we first performed a steady-state heat transfer analysis. Internal heat is generated by the center circuit assembly, and heat was applied at the extremity of the copper connectors at the extent of the circuit board. As I can show here, we have our heat generation, and we have the surface heat sources at the extremities. Convection properties were then added to the circuit board itself as a means to cool the assembly. And then we ran this analysis, and you can see the temperature changes that we had here. Next, we did a static stress analysis, and one of the really neat features here is I was able to go directly create a new design scenario. Go into my analysis parameters. I created a multiplier for one for the thermal, and then I went right to the thermal, and I was able to bring in my loading directly from the previous design scenario. The first design scenario was a steady-state heat transfer, And now what I'm doing is a static stress in order to generate my fatigue cycle. So then we switch over, we run the analysis, and this shows us the von Mises stress. And you can see where we have different points of concern. And really what we want to find out is how long are these circuits going to, how long are they going to survive? How long are they going to last? So we're going to go back into the FEA editor. And I can go into this analysis here. And right here I have the fatigue wizard or fatigue analysis. Which takes just a moment to load. So here on the first step, we can either do a strain-based fatigue life, or we can do a stress-based fatigue life, or we can do a fatigue safety factor. We're going to do ours based on strain, not stress. This is because we expect kind of a lower stress cycle, and it is expected to be closer to a plastic kind of behavior rather than an elastic type behavior. So we're going to go with strain. For some reason, it likes hopping off my screen. So on the next step here, I can type in, and the parts that we're considered or that we are concerned about are copper. So we'll call them copper, and we'll put in some data. Here we'll just leave this factor as 1. We have no real stress concentrations that we are concerned about. So now I'm going to open up, and I go into the fatigue wizard here, and I am going to grab a pattern, this very simple pattern, such as this, and it brings in that time history for that load. Here I can put in a desired life, and so we're just going to throw out a number to see what happens. We can either go by safety factor, or we can go to cycles to failure. We're just going to see what it goes. And then, because we're only concerned about one part, I can turn all the parts off, turn this part on, and then I press this button, and it's going through and it's doing my fatigue analysis for me. And you can see it's fairly quick. And now it's telling me exactly how long they expect each of these things, how long they expect the assembly to last, how many cycles. And obviously, it's going to last for quite some time. And it can even go node by node to give me a better idea of what I'm looking for. So once you're done and you're happy with these results, you can press finish and close out. So next we will discuss a mechanical event simulation of the container that is lifted off of that flatbed trailer and then is dropped, creating an impact load. So let me pull up that file. So here's my truck and my container. And one of the first things that we do is if I go into the parts, I can actually set up under my truck frame. I have a 3D kinematic part, which actually allows it to go through this mechanical event simulation. And I have set up nonlinear materials. For instance, the ground is concrete, which does not behave in a typical linear fashion. So we are incorporating all that into this analysis. Next, what we did is we went through and we created prescribed displacements laterally and vertically. As you can see, no, this one is the lateral and then vertically. And then I was able to go into the analysis or the setup, go to the parameters. Go into my load curves, and the first load curve is just the normal gravity that's going on, so there's nothing exciting there. But if I go to load curve 2, this is my horizontal load, and you can see I'm having it applied after 5 seconds and going till 8 seconds, and I can even view the plot of how that will be applied. And my third load curve is actually my vertical movement, and you can see that's applied for the from second time at 2 seconds to a time of 5 seconds, and you can see my plot there, plot here as well. So I can set all that up ahead of time and then run it through the analysis. So this type of analysis, it goes through, it goes step by step by step, and solves it at each point and basically iterates it until it comes to a convergent solution. So it can take some time, so I went ahead and I ran it, and then I have this brief video which basically shows you the movement of it as it comes over and then gets dropped. So that's essentially what we're modeling and what we set up. So if I go over to my results tab, I can step through at each time step and look at my forces and my stresses going on. And if I did very small discretized time periods, and I didn't want to step through all of them, I'm able to come over to Results Inquire over here, and I can actually pull up a maximum results summary. Which right now it's going through all the stresses that it found. And from here, I can figure out what part, what element, what node, and then figure out what are my stresses. And so as you can see here, if I'm assuming that it's typically like an A36 material on that container, I hit 40,000 just in this analysis. And so I would have some work to do going forward in terms of analyzing whether I need to change materials, make them thicker, or any of those other options that you have in the design and engineering cycle. So let me close out of that. And the last thing I have here, this is basically a vessel. I split it up into quarters to make my analysis easier and quicker. So, and it's held together, there's two sides to it, and they're held together by a flange that is bolted together. So there's 2 bolts here. There'd be a total of 8 since we're using 1/4 of it. I set up a symmetry constraint all along the outside, or I guess where it would match up. And then I have a nodal constraint at the end, just so this thing doesn't fly off. Then we apply a pressure to the inside. But in order to replicate and analyze and do the bolts, if I go over here to the mesh function, you can see here we have this cat addition, and this is a very neat feature. We either can put in a joint, which acts as a truss element, and you can either do this as a universal or a pin joint. And basically the difference is a pin joint has a node on each end and an axis that it rotates about, where a universal joint will actually have a center node that you can rotate almost as like a ball and socket type of joint. We also we can set up bolts, and there's 3 different ways that you can put in a bolt. You can have it where there's a nut on the back where there's no nut, or you can have it where it's grounded where it actually goes into a threaded part. Let me open up the bolt real quick. This is basically how I can go through and generate a bolt. I can create a part. I can set its diameter. I can specify where the bolt head is going to sit and what its diameter is, all the interior hole surfaces that will interface with that bolt, and then basically where the nut sits and the nut's diameter. I can also put in a preload, which I did on this for this analysis, which you can see here as my first and second constraint group. Then we run the analysis, and right here you can see my stresses. I can show a displacement, but really what I care about is what's going on in that bolt. So if I turn this around so that we're kind of looking at the bolts, I'm going to sit here and I'm going to isolate just these parts, and these are my bolts, or the model, the analytical model of my bolt. And I can go to this other results, go to element forces, and select my axial force. And if I position this, I can see what the loads are, and I see that red in there, so I know that that right is at that about 4,400 pounds, so about 4.4 kips. I can also go in here, and I can specify, or I can look up what my shear forces are in both directions, and then I can take those loads and I can throw them into an interaction equation and determine the adequacy of my bolts. So this is powerful because you can do all different kinds of complicated bolted geometries and bolted connections, and then analyze to figure out which bolts are taking the most force, and figure out what is your critical bolt, and then design based off of that, and then go back through the program and change it. So if I specify, for instance, that these are 1/2-inch bolts and I needed to upgrade them, I can go back in, model them as a 5/8 or a 3/4 inch bolt, or even increase their material properties and run it again to see what the effects are on my entire assembly, rather than just having it sit there and be a truly rigid element. So now I'd like to briefly discuss the 2016 additional features. So I'm going to send it back over to you, Mike, just so that you can show your desktop.
Thank you, Mark. And you should be seeing that now.
Yes, thank you. The first thing is, with the 2016 products, Autodesk has included Sim Studio. This is a way to bring in, you can create, modify, simplify, and repair CAD models of many different types of formats. Kind of what we were looking at before in terms of the CAD neutrality, this takes it another step. Not only can we open different CAD data from different sources, now we can actually manipulate it and get it ready for analysis. So if somebody designs something and we need to simplify it, we don't have to go back to the native CAD environment. We can do it in the Sim Studio. Also, I'm very excited about this. From Autodesk Inventor, I can now bring in welds as a separate part and analyze them so they can have separate properties and geometry, and then I can change them actually in the simulation mechanical environment. The other big thing in terms of importing are 3D sketches. With the 3D sketch coming into Sim Mechanical, you now can bring that in and use that as your framework for doing beam elements and doing structural type analysis. They have realized at Autodesk that people like drawing in their native CAD environment more so than in SimMech. You can draw in SimMech, but this just brings in that ability to take in a stick figure and then go through and apply your element features or your element properties to it and do your analysis. They've also expanded the global mesh refinement. One of the things is that we can go through and we can do convergence studies, and we've been able to move that to thermal and electrostatic analysis now. And the last thing that I want to highlight is the remote solving capability. With a remote solving, if you have a network license and multiple licenses, now you're able to actually set up your model and send it off to another computer. So if you have a server sitting around that has much better processing power, you can now send it there to have it solved. Or even better, you can send it to your boss and his computer, because obviously he never does anything like you, so somebody needs to utilize his computer. So those are the 4 big things that just came out with Sim Mechanical 2016, which just got released this week. We're very excited about it. There's obviously more Nastran capabilities that have been built into it, and it's only going to get better since we've been able to add that Nastran notoriety and proven effectiveness and accuracy.
Mark, due to a technical difficulty, we were not able to hear when you were commenting about the expanded global mesh refinement. Would you mind repeating that, please?
Oh, sure. The global mesh refinement, basically, it's able to do it during stress analysis currently, or I should say last week it could do it mainly in the stress analysis, and now they've moved it, or I shouldn't say moved it, they've expanded the capability of it so that you can actually do it in thermal and electrostatic analysis. I didn't study English, I studied engineering, so pardon me if I don't say something correctly.
Pardoned, and thank you for reviewing that again. So, and I suppose a lot of you are wondering, what's the next step? In order to, one of the services that Master Graphics and Applied Software provides is a simulation business process assessment. And that is where we come with a team and we interview your key stakeholders, such as, you know, your R&D department, your leadership team, quality, operations, and various components that are in your business process. We will review your business drivers and evaluate the company objectives. We identify improvement opportunities, and then we provide a viable roadmap from start to finish along with a return on investment so that leadership can make a good financial decision. That is, you know, something that needs to be scheduled and with the approval of senior leadership. So now we have a question and answer time, and if you would like to type in any questions at this point, that is great. And as of right now, our attendees do not have any questions. So we would like to thank all of you that attended. And a couple of things, there will be a recorded webcast that will be available for your review, and that link will be provided via an email. Your account manager will follow up after this session to discuss the next steps. And we would like to thank you for joining us today. We hope that you have found this webinar informative and helpful to your business. Thank you.